Hello, I've got a second order modeling example here for you. So an instrument packet is dropped from a cliff on a planet with very strong gravity and a thick atmosphere. So we're not going to neglect air friction, we'll include air friction. The position x of t measured down, here's a picture, here's the cliff, here's the mass being dropped, satisfies the second order ordinary differential equation. The acceleration, d squared x dt, equals minus 3 times the velocity, dx dt, plus 60. So there's the gravity term, which is a constant force. And here's the air friction. The air friction is a force that opposes the velocity. If dx dt is positive, then the force is negative. And if dx dt happened to be negative, if it were moving up, then the force would be positive. Okay. So we're supposed to find and solve the initial value problem for the velocity y, which is dx dt. Okay, so dy dt is the d dt of dx dt, right? Because y is dx dt. But this is just another name for d squared x dt squared. In fact, that's kind of why, if you ever wondered why the 2's are where they are, it comes from this. And that's equal to minus 3 dx dt plus 60. So that's minus 3, but dx dt is y plus 60. Okay, so that's the differential equation. And what's the initial condition? Well, a lot of times like this, they don't give you an equation. They use a word like dropped. You didn't throw it down, you didn't throw it up, you dropped it. So if you drop something, you start with velocity 0. So that is y of 0 is 0. So we've got our initial value problem, and now we've got to solve it. So we can get rid of that part, because everything we need now is here. Dy dt equals minus 3y plus 60, and y of 0 is 0. Okay, so actually, this kind of thing happens a lot in modeling. The rate of change of some quantity has a term that's proportional to the amount of quantity there is, plus a constant term in this. So the change of the velocity y, with respect to time, there's a friction term that's where the acceleration is proportional to the velocity, plus the gravity term. So I'm kind of glad we did this, because I've been talking about the equivalent differential equation all the time, but I've never got there from here. Can't get there from here. I don't know if you ever heard that expression, but anyway. So the way to solve something like this is you factor out the 3. So it's minus 3 times y minus 20, right? Because minus 3 times minus 20 is plus 60. And then we have y of 0 equals 0. All right, well, I'm not good. So this is the exact same differential equation we've been solving a lot. I don't know if we've got that initial condition yet, but I'll just say here by inspection, we have y of t, or sometimes you can just write y of t is 20 plus a constant times e to the minus 3t. And now we want to impose the initial condition. Y of 0 is 20 plus c e to the 0, that's 1. So that's 20 plus c, and that we're going to set that equal to 0. That's a pretty easy one to solve. C is minus 20. So So we get that the solution to the initial value problem is y is equal to 20 minus 20 e to the minus 3t, or y is 20 times 1 minus e to the minus 3t. Either one is good. You don't have to put both of them. Either one is good. And it's probably useful to draw what the graph looks like. If I have t here, and this is y, let's put 20 here. The asymptote is 20. If I wait a long time, the velocity will reach 20, which is the terminal velocity, and I approach like that. Well, I approach 20 exponentially. In fact, where does time go on here? Well, we've talked about this before, that I get about the initial distance gets multiplied by 1 over e, or about a third, after when that exponent is 1. So here we have time of a third is right about here, where this distance goes from 20 to about a third of 20, or 1 over e times 20. All right? So it looks something like that. All right. Okay, so even though this started out as a second order ODE, the velocity satisfies this first order ODE, and thus we can use the sort of star of the show in this review, the same differential equation. Okay, all right, bye.